The Unreal editor is a what you see is what you get, or WYSIWYG editor. That means it provides multiple preview mode options to facilitate rapid iteration without actually running the game on the target device. It's important to know that this is not a substitute for actually testing on device, especially for performance. But since game development is hard, developers should take advantage of all the tools available. To change preview mode, select Settings, Preview Rendering Level, and choose between Shader Model 5 for Rift or Android ES 3.1 for Quest. There are also various performance visualization options that developers can use to get a rough sense of the performance situation. Some of these options are not available on Quest and can only be used with Shader Model 5. The following are two useful visualization options. The first one, under View Mode, Optimization View Modes, Light Complexity. This visualization option is Shader Model 5 only. It estimates the computational cost of lighting a pixel from all dynamic lights contributions. It is not recommended to use this visualization option to estimate Quest lighting performance, because the two platforms use very different methods to calculate lighting. Dynamic lights refer to the mobility section of the light being set to movable. And the second, View Mode, Optimization View Modes, and Shader Complexity. This visualization option is available for both Rift and Quest. It calculates the total number of pixel shader instructions a material would execute without lighting for each pixel. Even though the total number of pixel shader instructions sounds very precise and technical, it is actually not a precise indication of performance and therefore should be treated as such. To use Unreal Frontend, launch Engine, Binaries, Win64, Unreal Frontend.exe. Highlight your application under Session Frontend, My Sessions, then go to the Profiler tab and click on Data Capture. Click again to stop the capture. After stopping the capture, a prompt will show up asking if you would like to load the capture. Click on Load File. The capture contains all metrics UE4 collects during the execution of the game. It includes metrics from all stat commands like StatUnit and StatEngine. Outside of Unreal, there are many tools available that can offer a deeper level of information about your application. These tools require more preparation and have a steeper learning curve. Another tool is Systrace. Systrace is a general CPU performance tool that comes with the Android SDK. If you installed Android Works located here under the UE4 engine path, which is Engine, Extras, Android Works, Win64, you might find your Android SDK installation at C nvpack Android-SDK-Windows. Run monitor.bat under the Tools directory. With the app you want to trace highlighted, click on the button shown above. Let's be sure to set Enable Application Traces From and select the process you want to trace. As a recommendation, set a large value such as 10K for trace buffer size because the trace output can be very large. If this buffer size is not large enough to accommodate the capture, parts of the output could be lost, and if the lost information is essential for opening the capture process is a failure and an error message will show up. We're going to just trace for 5 seconds. Open the trace output, which is the trace.html file with a Chrome browser, and we will see this. Use the toggles on the upper right corner to switch between navigation modes. The first toggle enables selection mode. Use the left mouse button to select and inspect events in detail. The second toggle enables panning mode. Use the left mouse button and drag to move the timeline view around. The third toggle enables zoom mode. Use the left mouse button and drag to zoom in. And the fourth toggle enables timeline measurement. Use the left mouse button to indicate the endpoints you would like to measure on the timeline. To instrument your CPU code for Systrace capture, use the scope_named_event macro in your code to annotate a section of your system with a name, and the timing information will automatically show up in the Systrace capture. One example use of this macro can be found at Engine, Source, Runtime, Launch, Private, Launch Engine Loop.cpp on line 4266. So that's one such macro used. It's using the label f-engine loop tick. GPU information is also available on systrace. To view GPU traces, follow the steps in the documentation we have linked below. To start a systrace capture with GPU information, type in this adb shell command, adb shell ovr GPU profiler -e. Type in this command prior to starting your game. And then start your game. Run it like the normal systrace. The only additional option to select is GPU render stage, which is selected here. We're going to trace for 5 seconds. With both application and GPU render stage selected, create a systrace capture and you will be able to see how the GPU executes in parallel to the CPU of the Oculus Quest. The top row are the GPU information, and then the bottom parts are the CPU information, and you can actually see and measure them, how much time has elapsed in between these processes. Our next tool is RenderDoc. RenderDoc is an open source project popular among graphics programmers. It can be used to profile Rift and Quest application using OpenGL or Vulkan or DirectX. Developers can download RenderDoc from the link included below. The installation is pretty fast because it's a very tiny. And then we're done. For Rift, the Unreal Editor comes with the RenderDoc plugin for convenient capture within the editor. To enable the plugin, open Settings, Plugins. Type RenderDoc in the search field. Check the Enable checkbox. Restart your editor for the change to take effect. Once the editor restarts with RenderDoc enabled, you will see the RenderDoc icon on the upper right corner. Click on the button to make a capture and RenderDoc will launch automatically. With RenderDoc open, double-click on a thumbnail to load a capture. Once it is loaded, the OpenGL, Vulkan, or DirectX draw calls made by our application are shown in the event browser. Click on the clock icon to replay the draw calls and measure their durations. Because the duration is measured by replaying the commands, it is important to make sure that there are no background processes that might use the GPU heavily. UE4 supports annotation during draw call submission. Therefore, all draw calls captured by RenderDoc are grouped into different sections with programmer-provided labels. The sections correspond to the draw call submission process and can be found with text search in Visual Studio. If you find a draw calls label to be not descriptive, you can also use the geometry and texture panel to inspect the mesh and where it was rendered on screen. A detailed explanation of every section entails a deep dive into UE4's rendering process and would be outside the scope of this learning path. Instead, we will explain a few simple sections. Scene, this group denotes an entire frame's draw calls. Draw calls outside this group are likely related to debug systems. Prepass DDM_all_opaque. This group represents the Z prepass UE4 uses to prepare the depth buffer. This serves as an optimization as well as a prerequisite for the defer shadow map technique. Shadow depths. This group contains all the draw calls for the generation of the shadow map. Base pass. This group contains all the draw calls of the actual geometries in the scene. With preview rendering level set to shader model 5, this is what is known as the G buffer pass. On Quest running forward rendering, this group represents the actual geometry rendering because UE4 runs a forward renderer on Quest. For Quest, with RenderDoc open and Quest connected to your PC via USB cable, click on Local on the lower left corner and select Oculus Quest. From Launch Application, click on Browse and select the application you want to debug. Note that in order for RenderDoc to connect to your UE4 application on Android, you need to make sure your project is not marked as for distribution in the project settings. Click Launch to start your application. Once RenderDoc establishes a connection with your app, you can make a capture by clicking on the Capture Frame button. Please refer to Course 11 on how to identify expensive assets and improve performance using RenderDoc. Optimizing an app is a big process, so here are some things to consider when running these tools. Eliminate external factors that can cause performance differences. The first one is the dynamic clock system, which will by default upclock the CPU and GPU if your application is a meeting frame rate, or downclock if the application is very well performing and doesn't need its current frequency. This ADB shell command will lock the CPU and GPU clock level to 4, which is the maximum on the Oculus Quest. A developer can choose other settings such as 3 if that's more representative for the game. The thing that matters is that they're locked. The goal of locking these numbers is so that we can get consistent readings from our profiler since the Quest runs at a variable clock rate by default. For detailed performance testing in a specific spot, it can be useful to lock the camera in place both rotationally and positionally so that the user's HMD position doesn't influence the rendering. Oculus provides 2 blueprints to stop the positional and rotational tracking. It is important to be aware of how a tool collects and presents data. Some tools modify the data to make it easier to read, but the accuracy and precision will be lost. For example, sometimes in-game performance data is presented as an average over multiple frames because drawing a rapidly changing number on the screen is very difficult to read. Being aware of such nuance is often the key to identifying performance issues. And there we have it. Now that you have learned an overview of the tools available to us for optimizing our app, in the next course, we will be demonstrating how to utilize them in your app.